Good evening. We start a review. Now, I left my other camera at home, so today I only have the document camera. On the right hand side you see it's only the screen of the calculator, because right now you should know how to enter the buttons. And the list of the question, the list of the topic that we'll cover is also on the right hand side. So the first part of the topic is subspace. Let me subspace question. Let me just go the overview first. In terms of subspace, you will see something like this kind of question. Also this like 2 and 3 here, because it's very difficult to verify it is a vector space, because we need 10 axioms. We only verify the subspace here. So the question for the subspace will be 1, 2, 3. Yeah, 1, 2, and 3. Right. So it's not the vector space. I just changed to subspace because we need to verify those 3 things only. So the first question, number 1, determine which of the following set is a subspace of the polynomial of n degree or less. So we've looked at the first question at the polynomial of the form a plus bt squared. So in that case, we're going to check these 3 things here. It has the 0 vector, because if we let a equal to 0, b equal to 0. So if a is equal to b equal to 0, we have the vector 0, which is good. And with that, we will not verify, but it will be closed under addition and multiplication. This 1 degree exactly 4, meaning that we have to have something t to the 4th power. This term cannot be equal to 0. So because of that, there is no 0 vector here. So B, this one has no 0 vector. Because of that, it is not going to be a subspace. Same thing here, at most 4, which is okay, but it has a positive coefficient. Positive is not 0, so therefore this doesn't have the 0 vector either. So in this case you only have A, because it has the 0 vector. Those two does not. Those two do not. Right. 2 and 3 will verify a little more details, all 3 of them. Right. So go to 2 and 3. To determine if H, the set of all the points in this form, form a subspace of R2. Right. So first, the vector will be in this form. We verify those 3 things. So for A, we have the vector s and s minus 1. We ask ourselves, does this equal to 0, 0? And the answer is no. It cannot equal to 0, 0. Because if s equal to 0, we have 0, negative 1. If s minus 1 is 0, we have 1 and 0. So this point cannot be equal to 0. So because of that, it is not a subspace. Because there's no zero vector. We do not need to verify these two. Now on the test you will see one question. We have to show that it is a subspace. So we will have something like number 3 here, and we have to show that it's actually a subspace, meaning that we need to verify all 3 things. I'll take sometimes. Right, first, the vector is in this form. Now we see that when s equal to 0 and t equal to 0, we have a vector 0. If s equal to 0 and t equal to 0, so yes. So this, the first properties is satisfied. So we have a 0 vector. Next, we need to show that it is closed under vector addition. So first we have the 0 vector. Right, to show that it has it closed under vector addition, we're going to write 2 vectors and we just add them. So the first one is s1, 3s1, and then t1. So we just say 3 different values for s and t. So s1, 3s1, and t1. And then we will add s2, 3s2, and t2. So pretty much we just add the subscript here. Right. Notice that a vector is in H if the second component is 3 times the first component. So we take the first one, multiply by 3, and we have the second component. So there is the relation like that. When a vector has that relation, then that will belong to H. Now we know this belongs to H and this belongs to H. When we add these two, just standard vector addition, s1 plus s2, 3s1 plus 3s2, t1 plus t2. I will factor out the 3. Now we see that the result vector, we have the first component multiplied by 3 give us the second component. Because of that, the result here we say belongs to the set H. So which means if 2 vectors in H, when we add them, we also have a vector in H. So yes, so that one closed under vector addition. So put a check mark here too. And then C, close under scalar multiplication. Once again, we start with a vector belongs to the set H. So we just have the first one, first component. The second component is 3 times that. the third component could be anything, right? So this vector is in H. Now if we multiply by a constant k to it, we're going to have ks, 3ks, and kt, right? What we see is this vector, if we take the first component multiply by 3, we get the second component. Because of that, this vector is in H. So any vector that has the properties of the second component is 3 times the first component, that is in H. So we start with a vector in H, we multiply, we also get a vector in H. So now we satisfy that as well. Because of that, we say H is a subspace of R3. So that's the first part of the test. First topic for the test is about subspace. Again, those need to verify those 3 properties. Alright, next we have linearly independent. We get back to number 4 later. Now we go to linearly independent, right? So that will be question 6, 7. Determine if the following vectors are linearly independent. Right, this is very simple. Set of vectors are linearly independent. We have a lot of equivalencies. But the easiest one is to use the determinant. So we have 2 vectors here. 3 polynomial. If we're going to put that in the vector, 3 vectors. We start with the constant is 1, and then 0t and 0t square. So 1 will be like 1 plus 0t plus 0t square, and we put that in the column 1 0 0. T square will be 0 0t and 1t square, and then this will be 2 3 and 0. So we have 3 vectors. Just find the determinant 1 0 0 0 0 1 2 3 0. So just find the determinant. How far? Zoom. That is 3 by 3. Right. So just put that in 1. Do not hit enter here. 0 2 3 4 and determinant of that is -3. If it is not equal to 0, then it will be linearly independent. And then of course we can do the same thing. On the test you will have to use the wrong skin for at least one of the problem. So we can also use the wrong skin. The wrong skin, when we do that, we can just say is the function. The first row is the function. Just say like this. We can say P1, P2, P3, and then the second row will be the derivative. And we just stack the derivative so that it will be a square matrix. So we require to have the second derivative. And we take determinant of that. Of course we can do the same thing as we did before. Right. So t will be just t, derivative is 1, 0, t squared, 2t, 2, 2t, 3t squared, be 2 plus 6t, and then 6. Of our determinant, and this is should not be equal to 0, then it will be linearly independent. It is not equal to 0 for every t, I should say. Not equal to 0 for every t. Right. I'm going to do the 2/3 determinant with t like this. Of course, we can also just do it like this one. But notice that we do not need to go any further. On this problem, we see that this is 2t plus 3t squared. So that obviously is going to be 2 times P1 plus 3 times P2, because P3 equal to this, so it is not linearly independent, or we say linearly dependent. It is linearly dependent because P3 can be written as a combination of P1 and P2. If you can say that, we don't need to do any math. Of course, we can use the wrong skin. Sometimes might be a little bit more work, or just stack in the vectors if it's possible. Of course, if we have e to the x sine or cosine or anything like that, the wrong skin will be an advantage. But polynomial, we just use stack that as a vector. That would be better. Alright, and the next one we do the same thing. Just stack in the vectors. Stack the vector in the matrix. That's what I would recommend. Determine whether this set is the basis. Of course, now in order to be a basis, there will be two things here. Have to be linearly independent. And it has to span the space that the vector is in. Right. But on this special case, if we have the same number of vectors as the dimension of the space it is in. Like here we have three vectors. We have three vectors in R3. R3 of course is three-dimensional. Now if we have the same number of vectors in dimension of the space those vectors are in, then all we need to do is linearly independent or spanning or both, but we only need one of them. So if we have the same numbers of vectors as the dimension that they are in, then we only need to verify linearly independent will be enough. So in which case linearly independent will imply the basis. We don't need to verify the spanning because it will span as well. Alright, so pretty much we just find the determinant of these vectors we put in the column. And we take the determinant. Would be the first one. Alpha zoom -2 1 4 so this is equal to 0. So if it's equal to 0, then it is not linearly independent. So the answer it cannot be a basis. We can also do the reduced Row-Echelon form. So instead of the determinant, as you see, we have a free variable here. So there's a free variable. There's a free variable here. So that's why it cannot be. It cannot be linearly independent. It cannot be spanning because we have the same number of vectors as the dimension. Right. But that is that. But there will be more about the basis. Right. Next, if we are given a vectors, a matrix, we should be able to find the node space, the column space, and then the row space. Right. So this will have a lot of questions in this topic. And then 8. And then 12, 13, 10 and 13. So there will be a lot of questions for this topic. We're not going to do all of them. Right. First, the null space. To find the null space of A, pretty much we just solve the equation, the homogeneous equation, make that equal to 0. Right. So all we need to do is I'm going to put this matrix and then we do the reduced Row-Echelon form. We really don't need the last column, but we'll just do that anyway. Right, it will have 2 rows, 5 columns. Okay. Right, 1, -2, -5, -3, 0, 1, 1, 2, right, that, and pretty much, yeah, not much here. So we have this. What we see here is that there will be 4 columns, each one corresponding to, let's say, x1 to x4, and x3 and x4 do not have the pivot entry, so they are free. So x3 and x4 are free. And then we can say the first equation equivalent to x1 minus 3 x3 plus x4 equal to 0, and x2 plus x3 plus 2x4 equal to 0 for the second equation. And if we put that in terms of solution, as a vector, we will have x1 will be equal to 3x3 minus x4. We have to move them to the other side. x2 will be negative x3 negative 2x4, and x3 and x4 are free. Right, with that we can rewrite as x3 3 negative 1 1 0 plus x4 negative 1 negative 2 0 1. So we say that the null space of A generated by these 2 vectors, and so that is a 2-dimensional object in 4th-dimensional space. Or we can write as null space of A is the spanning of these 2 vectors. that is the null space. The column space and the row space, it will be easier to do. So after this we go to so on number 4, all we need to do is we take A times U. If it is equal to 0, then it is in the null space. If it is not, then it will be null. On the test I won't ask anything, that is simple. Right. So that is the null space. This is what we have for the null space. We just solve this equation. Alright, the column space or the row space. All we need to do is either the rows reduce echelon form, row echelon form, or reduce row echelon form. On this one we already have the row echelon form ready, because this is, they said they are equivalent, and this is in row echelon form. So we see that the pivot is here, here, and here. Now we find the basis for the column of A. We see that the pivot is on the first column, second column, and the third column. So we just pick the first 3 vectors. So those 3 vectors will be the basis for the column of A. So pretty much will be the same where the pivot are. So we can say column of A will be just, I should say span of those 3 vectors. That is the column space. By the way, the row space will be those 3 rows. Right. This further dimension of the subspace kind of stand out from out of nowhere, but if we rewrite this, we will have A, so will be just, if I just write the vectors, will be A times this 1A, 0A over the second one, -3 and 0. So that is the first vector. The second vector will have B, should be 3, no B here, -9 and 0 here. And then C, 0 there, 1, 4, -1. And then D, 4, 1, -8 and -1. Even though it is generated by 4 vectors, doesn't mean that the dimension will be 4. So what we have to do is just put this in the vectors or in the matrix and do the reduced row echelon form. So when we do the reduced row-echelon form, this is what we have. Notice that this one we only have 2 pivots. So the dimension will be just 2. We cannot just say there are 4 variables. That will be 4 dimensions. We actually have to do it. Do the reduced row-echelon form and find how many pivots do we have. Alright, 10 will be easy. This matrix is in the reduced, not reduced, because there's still a 3 on top of this one here. We do have 3 pivots here. 3 pivots, so 3 pivot rows, 3 pivot columns. So the dimension of row space and the dimension of column space will be 3. So let me just write down 3 pivot, meaning 3 pivot column. So that will give us the dimension of the column space. That will be the rank, by the way. So we say dimension of the column space of the matrix A equal to 3, which is the number of the pivot entry. Alright, which is the rank, by the way. And then next, we'll see that it has this 1, 2, 3, 4 free variable. So in that case, the solution of the homogeneous equation we have 4 dimension, will be in 4 dimension. So in that case we say the dimension of the null space of A will be equal to 4, and that also called the nullity of A. And in general, the null space plus the rank, the nullity plus the rank equal to the number of columns 1, 2, 3, 4, 5, 6, 7. So that equal to 7. And that's what the rank theorem. So we say nullity plus rank equal to n, which is the number of columns. We'll get back to this, but this will be very simple. A column is either the pivot column or a free variable, and those add up must be the number of columns. Right. We get back to this. Now we go to 12, maybe 13. Let's look at 12. So this problem, by the way, you will see this kind of problem. We find the null space, column space, and row space. Right. So first, the null space of A. That is where we solve the equation, the homogeneous equation. Right. So we put in the augmented matrix. this matrix is in the row echelon form already, but we will do the reduced row echelon form here. Like that. So that's what we have. And here we have the three variables on the third column. So we say x3 is 3, and then we have the equation x1 plus 2/3 x3 equal to 0, x2 minus 1/3 x3 equal to 0, and x4 is equal to 0. So we write the solution in terms of x1, x2, x3, and x4. X1 we're going to move the 2/3 x3 on the other side. It becomes negative. And then 1/3 x3 to the other side. x3 is 3 and x4 is 0. Factor out x4, we will have negative 2/3, 1/3, 1 and 0. Right. So the null space is generated by just this vector. We can write as null space of A as the span of this vector, or better yet, if we multiply everything by 3, we will have negative 2, 1, 3, and 0. So we don't have to deal with fraction. So if we multiply by 3, we should have that. So that is null space. We just solve this equation. The column space and the row space will be very easy. What we do is we just write the matrix and do reduced row echelon form. We already did that though. This is the result. But let's just write. If we take A, perform the reduced row echelon form, we should have this vector. Not the romantic matrix though. And what we see here is the pivot is here, here, and here. So that's where we have the column space of A. Will be the spanning of not these three vectors, but the one from the beginning, the original matrix. So we'll be including 1, 0, 0, that's the first one. 2, 3, 0 for the second, and negative 2, 3, and 1. So we just find where the vectors corresponding to the pivot columns. So it's not this, but the columns from the beginning. The row space will be the spanning of these 3 rows. For the row space, we can actually just use this row. So for the row, we just write like this. And that's what we have. So that's how we find the node space, the column space, I should say the row space of A. Should be able to find those 3 spaces for a given matrix. Right. Next we go to the rank theorem, kind of the same idea here. The rank theorem, we will have something number 14 here. I just give that a moment. Right. So the rank theorem is what we have here. The nullity of A plus the rank of A equal to n, which is the number of columns. Now keep that in mind. So here we have A is a 5 by 9 matrix. So because of that, this matrix A we have is 5 rows, and 9 will be the number of columns. Right, and then we go to the rank theorem. We say the node of A, nullity, the dimension of the node space, plus the rank of A must be equal to n, which is 9, the number of columns, to say 9. The nullity of A is the number of free variables. And the rank of A equal to the number of pivot column. Of course, the pivot column is also the number of pivot rows. And when we add those two together, must be equal to 9, the number of columns. Right. What we see here is we have the matrix 5 by 9, so we have 5 rows. So at most we only have 5 pivot rows. So we say at most 5 pivot row or 5 pivot columns. So this is at most of rank A here, at most of 5. That means the node A had to be at least 4. So that's why we're going to choose C. Because this at most we have 5, so node A have to be at least 4. So have to be 4 or more. So that's what we have. Again, that theorem is the nullity of A plus the rank A equal to n, or we say the number of free variables equal to the plus number of pivot columns equal to the number of columns. So like we mentioned before, a column is either has a pivot or it will be free. So when we add those two numbers up, it has to be equal to the number of columns. Now chain of bases. For chain of bases, I highly recommend that you will look at the last example we have in the note, because there will be one question like that. Other than that, here's what we can do. So two things we can do in the chain of bases, two important things here. The first one is to find the change of coordinate matrix. So in this case, we find the change of coordinate matrix from B to C. Notice that the notation for that is going to be the script B, P, and we go from B to C. So the matrix P go back from B to C. The reason that we have to write this way, so it will be very easy to find. The way to find that, we just stack the basis of C will be C1, C2. So we're going to have C. So that is the matrix C on the left and B on the right. So the order will be look exactly like this: C on the left, B on the right. So this is pretty much the basis of C, and this is the basis for B. Once we do the reduced row echelon form, we will have the identity matrix first, and then the second part of it will be the chain of coordinate matrix from B to C. So just do the reduced row echelon form of this one. Of C, and this is the basis. So reduced row echelon form. And so we have just copy it down. Alright, so that matrix is equal to this matrix. Right. The advantage of that chain of coordinate matrix is if we have a vector in C is equal to change from B to C times the vector in basis B. So from B we multiply by that matrix, we get to C. It get the vectors in C. Right. Of course we can do that directly, or we can write vectors directly in this form. Suppose that x of b is equal 1, 2, write that in x of c. So here what we can do first, the vectors in basis b is 1 and 2, meaning that we're going to have 1 times the first vector of b plus 2 times the second vector of b. The first vector of b is c1 minus 6c2, and b I should not write as the vector form, sorry. Should say 1 b1 is c1 minus 6c2 plus 2 4c1 plus 3c2. So multiply out combined like terms, we will have c1 and ac1, so that will be 9c1 negative 6 minus 6, so it will be plus 0 c2. So this one's easy, so we don't have to do much. We just say it's going to be 9 and 0 in the basis of C. Like I said, you should look at the last question, the last example that we did in class that have the chain of basis. So there would be one question like that. This is simple. Right. Alright, next eigenvalues and eigenvector characteristic equation. This is rather more important. Right, so first let's just review quickly eigenvalues. We will solve the equation determinant of a minus lambda I equal to a number 0, and the eigenvector or eigenspace or eigenvector we will solve the equation a minus lambda I times the vector v equal to the 0 vector. So one of them is numbers, the other one is a vector. Right. So all we need to do is very simple. We just solve that equation. So we will have a determinant matrix A and then we minus lambda I. I is the identity, so pretty much we just subtract the lambda on the diagonal. And determinant, I use 2 vertical bar, and that equal to 0 number. Sorry, this question we already given the eigenvalues, so we need to find the eigen. Sorry, it look like there's a lag. I think it's okay now. So again, we are given the eigenvalues already. We just need to find the eigenvectors. To find the eigenvectors, we solve this equation. So the matrix itself minus the lambda, the eigenvalues on the diagonal. And we make that equal to 0. I will do the reduced Row-Echelon form here. Right, we have that. Right. Change fraction. So here we see that V2 is going to be 3 and V1 minus 1/3. V2 is equal to 0. So we write the solution V1, V2. V1 will be equal to 1/3 of V2. V2 is 3. Factor out of V2, we have 1/3 and then 1. So to find the eigenvectors, we can just go ahead and choose this vector, or if we want to, we can multiply top and bottom by 3. We can just say it's going to be 3. I'm sorry, it's going to be 1 and 3. If we just multiply by 3 to make it into integers. The same question on the next problem. We're going to solve this equation, so we will have that matrix and subtract the lambda on the diagonal, so minus -3, so that's like +3 on the diagonal, and multiply by v, vector v equal to 0 vector. So I will write the augmented matrix will be 4, -4, -4, -4, 4, and 4. It looks a little strange, but that's alright. Augmented matrix, so we just draw a line and then 0. And then reduce Row-Echelon form. I don't have to do this because all those rows are multiple of each other. So the first row will be just 1, -1, -1, and then 0 everywhere else. What we see here is that V2 and V3 will be 3, and the first row will give us V1 equal to V1 minus V2 minus V3 equal to 0. If we write that as a solution, V1, V2, V3, it will be equal to -V2, -V3, V2 is 3, V3 is 3. So we can say V2 times -1, 1, 0. and v3 -1. Both of them should be positive. I'm sorry, when we move that to the other side. So that's what we have. Next, find the characteristic equation. The characteristic equation is pretty much this is the characteristic equation. We're going to solve that. Will give us the eigenvalues. So the characteristic equation is this. So what we do is we just subtract the lambda on the diagonal. And then we subtract the lambda on the diagonal. And we find the determinant of that matrix equal to 0. Right. The good news is this is upper triangular matrix, so all we need to do is just multiply everything on the diagonal. And that gives us the characteristic equation. We can multiply this out and simplify, but let's not do that. Right, so we haven't done much. The problem we should worry about is the problem where we are just given the matrix and we need to find the eigenvector, eigenvalues, and then the eigenvectors. I'm going to do 2 of them, but in terms of diagonal, like number 24. Right. So first, eigenvalues and eigenvectors. I do a more complicated one. Let's look at number 21 here. It's going to be a long problem. So first, I should put some numbers here. Eigenvalues. That is this equation, the characteristic equation. So we just have that determinant of that matrix. Where we subtract the lambda on the diagonal. Determinant of that matrix must be equal to 0. Well, that one is easy. We see that this one is upper triangular matrix, so we just have 1 minus lambda 3 times equal to 0. So eigenvalues lambda equal to 1. Multiplicity of 3. Next we'll find eigenvectors. Eigenvectors is we solve the equation a minus lambda I times the vector equal to the 0 vector. Now we know that lambda is equal to 1, so we're going to put 0 here. Put 1 in for lambda. So pretty much 1 minus. I'm just going to write that first. Now let's subtract lambda, which is 1, on the diagonal. When we do that, we have a matrix multiplied by v, we have a 0 vector. So we have 0, negative 2, 0, 0, 0, 0 everywhere else. And then multiplying the vector v, we can say v1, v2, v3 equal to a 0 vector. Right, let's do the reduced Row-Echelon form, which will be not much. We just have 0, 1, 0 here. Sorry. We just have 0 on that side. So except for that one, we have 0 everywhere else. So here we see that v1 is 3, v3 is 3, and v2 is equal to 0. So if we're going to write the solution, it will be v1, 0, v3, or we can decompose in v1, 1, 0, 0, plus v3, 0, 0, 1. And then we find 2 eigenvectors for eigenvalues. So this is one eigenvector, and this is another one. All the eigenspace has those 2 vectors. Do a similar problem, but in this form of the diagonalization. First of all, this will be we'll get back to 23 later, but first let's just go straight to 24. On 24 we asked to find to diagonalize a vector if possible. So pretty much we just need to find eigenvalues and eigenvectors, and then we just put in this form. It's a nice question because when we have the solution, we can check that easily. So we do the same thing: eigenvalues, eigenvectors, and those things. So first, eigenvalues. Eigenvalues is where we have the characteristic equation. So we have the determinant. Where we minus lambda on the diagonal, determinant of that must be equal to 0. Right. 3 by 3 determinant. This one we will expand along the second row. Right. So if we expand along the second row, we're going to have negative 4 negative lambda. Right. Now notice the sign chart. It could be plus, minus, plus, minus, plus, minus, plus, minus, plus. So for 3 by 3, this entry is going to be a plus. So of course 0, we don't expand, we don't use 0 at all. Right, so now we cover the row and the column. What we left with is 1 minus lambda times minus a minus lambda subtract 0 times negative 5. Oh, that's, sorry. 1 minus lambda times minus a minus lambda subtract 4 times negative 5 equal to 0. So the equation will be negative 4 negative lambda, multiply this out, minus h minus lambda plus a lambda plus lambda square plus 20 equal to 0. Now I just simplify first. Negative 4 negative lambda lambda square that gives us 7 lambda plus 12. Right. We should multiply it all out to solve for, and then we have the cubic equation. But rather doing that, I just keep factoring. I will factor out the negative from the first. We don't really need to do that, but because we can do that. So I factor out the negative out, we have this. Right, and then we have lambda square plus 7 lambda plus 12. That gives us lambda plus 3 lambda plus 4 equal to 0. Now we factor it. We can say that lambda equal to negative 4 multiplicity of 2, because we have two factors like that. And then lambda equal to negative 3. Right. So we have two eigenvalues. This one count twice. Next, we find the eigenvectors corresponding to these two. This one we might have two eigenvectors. This one we have exactly one eigenvector. Right. Eigenvector, the equation is a minus lambda I times the vector equal to the 0 vector. We do that both sides, of course. Right. So we have the vector itself. what we do is we're going to add minus -4 on the diagonal. Minus -4, just like +4. Times the vector v, say v1, v2, v3 equal to 0 vector, and reduce row-echelon form. Let's not do that yet. Let's just simplify the math. I need to zoom out too, because this is a long problem. We just need right. So 5, 1, 4, 0, 0, 0, -5, -1, -4, 0, 0, 0. Actually very simple. When we do the reduced row-echelon form, we just have the first row, really. I'll do that anyway. Right, so we have that. I try to write extremely small. So in that case, v2, v3 are free. And v1 plus 0.2 v2 plus 0.8 v3 equal to 0. So if we're going to write that, it's going to be negative 0.2 v2 plus 0.8 v3. v2 is free, v3 is free. Finally, we can say the solution can be written as factor of v2. We have negative 0.2 and 1, 0 here. v3 be 0.8. That is minus, sorry. Zero and 1. If we want to, we can multiply everything by 5. So let's just do that, so we don't have to deal with fraction. Multiply by, I mean, I should not write that as v2, v3. Okay, I just keep it like that for now. So we can, if we want to write eigenvectors, we can say the eigenvector will be, now we multiply by 5, will be negative 1, 5, and 0. And then we multiply by 5 again, negative 4, 0, and 5. So we have those two vectors corresponding to this eigenvalues, two eigenvectors. Next we do the same thing. We take the matrix A itself. And then we subtract the lambda, the eigenvalues. Subtract negative 3 becomes plus 3. So we have v1, v2, v3 equal to 0 vector. Alright, to simplify, we should have 4, 1, 4, 0, negative 1, 0, negative 5, negative 1, negative 5, and we write the romantic matrix, then reduce row-echelon form. Right, so we have 1, 0, 1, 0, 0, 1, 0, 0, 0, 0. Right, here we see that what we have is no pivot in third column, so V3 are free. First equation, V1 plus V3 equal to 0. And the second one, V2 is equal to 0. So if we want to write, it will be as V1 is negative V3, V2 is 0, V2 is 0, V3 is free. So just V3. Factor out the V3, we have negative 1, 0, and 1. So the eigenvector corresponding to negative 3, we can choose that eigenvectors. Finally, we're going to put in the diagonalization form. So in that case, what we can do is we can say A will be equal to PD P inverse. First, the matrix P will be the eigenvectors. So let's just write this one, and that one. Right, so that is the matrix P, 3 eigenvectors. Next, the diagonal matrix. We're going to put the eigenvalues corresponding to the eigenvectors. So first we use those eigenvectors. The eigenvalues is negative 4, so we should have negative 4 on the first 2 rows. And then the last column corresponding to this eigenvalues, so we're going to put negative 3. And because this is the diagonal matrix, so 0 everywhere else. And then we just put that matrix in with the inverse. Sorry, kind of run out of space here. Yeah. So this is P, D, P inverse. We just put that inverse. Now to confirm that, we will just multiply it out. Negative 1. Multiplied by the diagonal matrix. and we should get back the original matrix A. Right, when that happened, that means we did the problem correctly. So again, the matrix P will be the eigenvectors in the order appears of the eigenvalues. Eigenvalues, we put that in the diagonal matrix, but it has to be corresponding to the first row. The first column is the first eigenvector corresponding to the first eigenvalues, so they have to be corresponding between P and D, and we can check the answer easily. Right. One thing to note, here we have the eigenvalues. We should not have any problem with eigenvalues because we always have with multiplicity or add up to, in this case, 3. But let's just say on this problem, if we only have one eigenvector instead of 2, and we still have one eigenvector here, so we cannot diagonalize the matrix if we do not have 3 eigenvectors. If we do not have 3 eigenvectors, we cannot put it in this form. In that case, it is called a defective matrix. The last one, I just want to go back to 23 and just do one application problem. Why it is advantage to us to write the matrix in this form. Right. So the nice thing about the matrix in this form, I guess I can zoom in. Right. So if we have A is PD P inverse, now if we think about that, if we take A times A, for instance, PD P inverse, PD P inverse, so pretty much inverse and P multiply together equal identity, which we just say cancel, and we have P D P inverse. The diagonal matrix, when it multiply, it will be just a square of that diagonal matrix. So with that in mind, where we have A to the K power, which is the power of PDP inverse, we just keep multiplying this, everything in the middle cancel, so that will be just P D to the K power and then P inverse. Right, so we have P is 5, 3, negative 2, 10. And then we have the diagonal, I'm sorry, this is matrix A, not matrix P. Matrix P is this. 3, 1, 2, 1, sorry. D will be 7, 0, 0, 8. Don't forget that there's a K power. And then the inverse. Let's do that quickly. What is inverse of that? 3, 1, 2, 1. So 2 by 2. 3, 1, 2, 1. Inverse. 1, negative 1, negative 2, 3. Alright. And then because the diagonal matrix, when raised to the power, all we do is just raise the diagonal entry to that power. And then we just multiply row by column. So the first one give us 3 times 7 to the K power and 8 to the K power. row times column 2 7 to the k power and 8 to the k power 1 negative 1 negative 2 3. Again, row times column, rows times column, so we have 3 times 7 to the k power, row times column, minus 2 times 8 to the k, and then rows times column, negative 3 7 to the k plus 3 times 8 to the k, and then row times column, 2 times 7 to the k minus 2 times 8 to the k, and then minus 2 7 to the k plus 3 8 to the k. So that is the advantage of writing the matrix in this form. If it's possible, we can do a lot of calculation from it, and that simplifies a lot of things. So pretty much that cover everything we need to know for the second test. I mean the third test. I will not ask the question for the eigenvalues and the eigenvectors separately from this, because when I ask you to diagonalize a matrix, something like this, you have to find the eigenvectors and eigenvalues already. So in that case, you will see more of this form rather than just find the eigenvalues or the eigenvector. Other than that, I think I will end the video here, because we should cover everything we need to know. Alright, I hope you find this video helpful. Thank you for watching.